Hello everyone, I'm Hobin from Samsung Electronics. The title of our paper is SPFS on stacking a persistent memory file system on legacy file systems. Persistent memory has low access latency and byte addressability. Intel obtained DCPMM is the first commercialized PMM, and it has been used as an intermediate layer between DRAM and SSD. Even though it has left many positive legacies, Intel has killed the obtained business, unfortunately. However, there are several alternative products such as NVDIMM and MRAM. Also, it is expected that CXL memory devices will be available as the next generation PMM. In order to use PMM as an intermediate layer between DRAM and block devices, tiered file systems have been developed. Ziggurat and Strata are state-of-the-art file systems for tiered storage. However, they are monolithic file systems and they have a couple of drawbacks. First, since they manage all types of storage in a single file system, they had to reinvent many existing features of the mature file systems which are tailored for specific block devices or purposes. Second, the monolithic design adds complexity of managing multiple types of devices. Third, to deploy a monolithic file systems, we must back up our files and restore them in the new file systems. Therefore, we question this: can you reuse legacy file systems that have been improved for decades? Our answer to this question is that we should take a modular approach. Deploying a PMM-optimized stackable file system on mature file system is easier and more practical. Now, let me introduce the design of SPFS. SPFS is a stackable persistent memory file system which provides PMM as a persistent write cache to PMM-oblivious file systems. SPFS is an upper-level file system that can be placed on top of any file system such as ext4, F2FS, and XFS. We denote those block device file systems as X, and SPFS X means their tiered configuration. The main functional goal of SPFS is to observe order-preserving small writes using a small PMM. Other than order-preserving small writes, or other IOs are delegated to the raw file system X so that it can utilize many desirable mature features of existing file systems. There are two challenges in designing SPFS. First, SPFS must be lightweight because it duplicates the file system overhead. Second, SPFS must effectively classify small synchronous writes. To be lightweight, SPFS manages all metadata in hash tables. To manage extents in a hash table efficiently, we propose a novel extent hashing algorithm. Next, we propose a ready sync point profiler that profiles synchronicity and observes them into PMM. Without novel designs, SPFS X improves the performance of legacy block device file systems by up to 9.9 times. Now, let me explain how SPFS detects and steers small synchronous writes using sync point profiler. Ziggurat and SPFS use a similar profiling mechanism to detect synchronous I/O. However, the write size predictor of Ziggurat makes a block placement decision per write in an eager fashion, whereas SPFS makes a block placement decision per fsync in a lazy manner. Making a block placement decision per write results in storing even small asynchronous writes in PMM. However, asynchronous writes better to be stored in the faster VFS cache. The I/O type that the fast VFS cache cannot have is the synchronous small writes that require durability. Therefore, SPFS focuses on synchronicity as its profiling metric and profiles I/Os per fsync instead of per write. Let me show how SPFS RAID sync point profiling differs from rigorous eager write point profiling using an example. In this example, an application keeps writing small data and calls fsync intermittently. Since Ziggurat profiles each individual writes, small writes A and B are stored in PMEM. The following fsync is translated into a no-P instruction, and the next small write C and its overwrite C prime is also stored in the PMEM because their sizes are small. With this example, we can see that Ziggurat fails to leverage the fast VFS cache. Next, let me show how SPFS works differently. SPFS only focuses on the synchronicity. Each individual write is first stored in the VFS cache of the raw file system because the file's synchronicity is not known yet. So A and B bypass the SPFS, and they are stored in the fast VFS cache. When the first fsync is called, SPFS detects workload is asynchronous since its accumulated write size exceeds the profiler threshold. Therefore, the fsync flushes A and B to the block device. And the following write C is also stored in the VFS cache. However, when second fsync is called, SPFS detects the buffered I/O is small and consider the workload is small synchronous write, which is the target of SPFS. Therefore, it decides to promote the file to PMEM. Note that only extent mappings are migrated to PMEM at this time, and the data migration is delayed until the subsequent write is made. That is, when the next write C prime is called, it is stored in PMEM and completes the promotion of extent C. From this example, we can see that SPFS exploits the strengths of all layers based on the I/O characteristics. Specifically, SPFS maximizes the use of fast VFS cache and uses small PMEM space conservatively. SPFS not only promotes files to PMEM, but also demotes files from PMEM to raw file system because the I/O pattern can change dynamically. If the read performance of PMEM is lower than that of DRAM, as in obtained DCPMM, the promotion may degrade the performance if access pattern is changed to read intensive. SPFS uses a metric called the sync factor to sense the synchronicity of the active workload. Sync factor of file is gradually reduced if the recent access pattern is read intensive or if it is not small synchronous write. This formula employs an exponential moving average to give more weight to the recent accesses while attenuating older ones. If the sync factor drops below a threshold, SPFS demotes file and benefits from the fast VFS cache in the raw file system. Next, SPFS manages all file system metadata using a persistent dynamic hash table. One of the challenges in the hash-based metadata management is how to manage extent in a hash table. Now, let me present our novel extent hashing algorithm. An extent consists of contiguous blocks, but hash table is not designed for indexing range data. Suppose extent E with the start of that 3 and the length 7 is stored. Another hash-based file system called hashFS proposed to hash every single key in an extent. This requires a very large number of entries in hash table. Our extent hashing algorithm is different in that it founds the number of entries to a log scale. With this extent hashing, we can manage a much smaller metadata than block hashing. Extent hashing stores pointers according to the binary representation of keys. For each key in an extent, we calculate the stride length. Stride length is the maximum distance to the next pointer from current key. Stride length is calculated from the number of 0 bits next to the rightmost non-zero bit, which is called TNZ. For example, the TNZ of binary number is 1, 1 because binary number 1, 1 is 0 because there is no 0 on the rightmost bit. The TNZ of 100 is 2 because there are 2 zeros on the rightmost bit. And the TNZ of 1010 is 1 accordingly. In the example figure, the first pointer is inserted in bucket 1. And because the TNZ of 1 is 0, the next pointer will be stored in the next bucket. And the TNZ of 10 is 1. We skip one bucket and store the next pointer at bucket 4. And the TNZ of bucket 4 is 2, so the last pointer is stored in bucket 8. In this way, extent hashing reduces the number of pointers in a log scale. Next, let me explain how such algorithm works. We first access the bucket corresponding to the query key. If the extent is not found, we flip the rightmost non-zero bits and access the next corresponding bucket. In this example, we search key 7. If the extent is not pointed by bucket 7, bucket 6 is accessed. Since the extent is not found again, we flip another bit, and the extent is found at bucket 4. This algorithm guarantees search correctness at the cost of increasing search complexity. Now, let me present the performance evaluation. SPFS is evaluated on 2 machines. The first machine has 256 gigabytes Intel Optane DCPMM, and the other machine has 16 gigabytes NVDIMM. We deployed SPFS on top of ext4, F2FS, and XFS, and compared the performance of SPFS X against other file systems, including Zigglerat. In this experiment, we evaluate the insert and search latencies of file mapping structures using a micro benchmark. Along the x-axis, we vary the size of extents for fixed-size files. The average insertion latencies of extent tree and extent hash decreases as the extent size becomes larger. This is because the larger extents result in a smaller number of extents and the index size becomes smaller. In contrast, block hash suffers from the large extent size because each extent insertion requires multiple pointers to be stored. Its insertion latency is significantly higher than extent tree and extent hash. As for search performance, block hash is the best when the extent size is small. However, as the extent size increases again, block hash shows the worst performance because of its large index size. Compared to extent tree, extent hash shows lower search latencies. However, its search latency is higher than block hash because of its log scale search cost. In the interest of time, I did not explain the fast lookup optimization. Please read our paper if you are interested. With this fast lookup optimization, extent hash can outperform even block hash. Next, we evaluate the performance effect of stacking SPFS on block device file systems. In this experiment, we vary the ratio of buffered and direct IOs along the x-axis. ext4, F2FS, and XFS performance decrease sharply even when only 10% of IOs are synchronous. Nova and Ziggurate are insensitive to the ratio because they store all blocks in DCPMM. However, SPFS X shows much higher throughput than the others because it benefits from the fast FFS cache for buffered I/O while processing direct I/O using DCPMM. This result confirms that SPFS X benefits from steering IOs to the right device based on the I/O characteristics. Finally, we compare the performance of SPFS X with Ziggurate and other block device file systems using FIU trace on NVDIMM server. Conventional file systems, ext4, F2FS, and XFS suffers from high synchronization overhead for all workloads. SPFS X tiers small synchronous write to NVDIMM and therefore reduces the trace replace time by up to 9.9 times. Unlike SPFS, Ziggurate aggressively uses NVDIMM, so it crashes in Moodle and user 1 workloads because the NVDIMM is not large enough to absorb all writes. In the small user 2 workload, Ziggurate outperforms SPFS X because it does not have the stacking overhead, and NVDIMM is as fast as DRAM. While Ziggurate processes most of the IOs using the fast NVDIMM, SPFS delegates asynchronous IO to the raw file system. In conclusion, we designed and implemented SPFS whose primary goal is to absorb or preserving small synchronous writes. It is also designed to take advantage of the legacy block device file systems for non-synchronous IOs. SPFS manages all file system metadata in hash tables, and to reduce metadata size, we propose a novel extent hashing algorithm. With this design point, we show that SPFS X improves the performance of a raw file system by up to 9.9 times. Thank you for your attention. If there are any questions, I shall do my best to answer them.